Hi, my name is Lakshya Jain and this is my video for solution of maths end term examination question number 6. So let's begin. Right, so the question given to us that consider the ODE y double derivative plus 16y is 4 direct t minus 3 pi. Given that the initial conditions at t is equal to 0 y is 0 and y derivative at t is equal to 0 is also 0. So the first part of the question asks us that what kind of real life phenomena is captured by the direct function if this ODE represents a mass spring system, right? So before answering the question, let's see what basically is the definition of the direct function, and it is much better and appropriate to call the direct function as a generalized function or a distribution. So the direct generalized function or distribution is defined in the form that direct or del x minus a has a value 0 everywhere except at point A, and at the point A it peaks out and has a very high value that is infinity. So this is the basic definition of direct function that we have. So if we plot a graph of this direct delta function or distribution that we have here, then this is direct x minus a in the y-axis that we have, and this is x, let's say, and if this is the point A, then everywhere except A the value of direct delta distribution or function is 0, but at point A its value peak out or reaches infinity, like a spike. It's just like a spike. So this is our direct the definition and the graph of direct delta function. Now if we see this in real life situation, this direct delta function is just like an impulse, a force impulse, a short impulse. So real life, this is just like a short impulse, because impulse is what it is, just a force that is applied for a very short duration of time and has a very large amplitude. So in the same way, this direct delta function acts for a very short period of time that tends to 0, but has an amplitude or has a value that reaches or tends to infinity. So the real life phenomena represented by direct delta function that we have is a short impulse, right? So another property that I want to discuss of direct delta function is that if we integrate a direct delta function, this is dx, right, between the intervals which contain a that we have, then this yields us 1. And if we have a function that depends on x and is multiplied with direct delta function and is integrated with it with limits once again from b to c, and a is between the interval b and c, then this is given to us by the value of g at a. The condition is that a should be between b and c. Right now, another thing that I want to add, if we look at this general equation, the equation non-homogeneous linear ODE that is given to us, y double derivative plus 16y is equal to 4 del dx is there, sorry, del t minus 3 pi that we have here, right? So this represents a mass spring system, right, with external force as direct delta function, right? And external force as direct delta function. So due to this external force or driving force being a direct delta function, that means it acts for a very short duration of time and has a very high amplitude. The real life situation that corresponds to this mass spring system is like a hammer block, block on this mass spring system, or a hammer response on a mass spring system. So the phenomena that this this non-homogeneous ODE represents for this mass spring system is a hammer response on the mass spring system. So this equation, the solution of this equation has a motion same that we get if a mass spring system has an external force or gets an external force due to the release of a hammer, due to the hammer, right? So and in undamped conditions that we will see later, right? So this concludes our first part. The second part that we have states that without solving and just using your intuition, sketch the graph of the solution. Now, the given equation is this. If I compare it with the general mass spring system, general differential equation for a mass spring system, then I get to know that C, that is a damping constant, is 0, and this means that in the given equation there is no damping, as I just said earlier, and K 16, right? So this is an undamped condition. The mass spring system is in undamped conditions, right? Now, if we consider time before 3 pi, right? Now direct delta has a value 0 before 3 pi, always have a value 0 before 3 pi. Therefore the equation then becomes, OD becomes y double derivative plus 16y is equal to 0. Now, and since we found out that the damping constant is 0, the motion it would represent would correspond to an SHM motion, right? Now, since it corresponds to a SHM motion, observing this, we get that intuitively we get that solution of this homogeneous equation would be a superposition of a cos graph and a sine, of a cos function and a sine function, right? But due to the initial conditions that we have, we'll find out that before 3 pi, the motion, there is no motion, and y is 0, right? But after 3 pi, that means once the force has acted, the hammer has acted, or the force has acted, the driving force has acted. Now the motion would start, and therefore we would have the solution as a superposition of a cos graph or a sine graph, right? So basically we will have we could have either of the two after 3 pi, right? So after 3 pi, it can be a sine graph that we have here, y and t 0, or we can have a sine a cos graph after 3 pi, right, this way, and or we could have a superposition of the sine and cosine graph. Anyhow, right? Another way, which is a little qualitative but still could yield an answer intuitively, is if we look at this equation before the time before 3 pi, this homogeneous equation that we have, if we solve it using the characteristic equation, that is of the form lambda square plus a lambda plus b is equal to 0, where b is the coefficient of y and a is the coefficient of y dash, we get that the characteristic equation would be of the form lambda square plus 16 is equal to 0, and the solution of that auxiliary equation or characteristic equation is a complex number, right? And whenever it is a complex, the solution of complex conjugates, then we get that the solution would be the sum of a sine and cosine function, or superimposition of both these functions, right? Now, but if we put in here omega is 4 for this case, right? So if we put, so basically yh would become now a cos 4t plus b sine 4t. Now, if we try to find out the the value of y using our initial conditions, we'll find that y, both a and b become 0, and y for the given intervals between before 3 pi become 0. But after 3 pi, after the force acts, the initial conditions that now start from 3 pi become something like this, like at 3 pi the displacement is 0, but the mass spring system acquires the y derivative, the velocity, it acquires a velocity, let's say v, right? So now if we have yh as a cos 4t plus sine 4t, now if we put y is equal to 0, then it is b here, sorry, y is equal to, if you put y is equal to 3 pi, y is equal to 3 pi, then it becomes a cos 12t plus b sine 12t, and which corresponds to 0. So basically it gives a as 0, right? So what remains is that yh is of the form b sine 4t, right? Now we can find the value of b by derivating it with respect to time once, but what remains is the fact that this y would follow the solution, the motion of the mass spring system. Before 3 pi there would be 0, that there will be no motion, but after 3 pi the motion would be that of a sine wave. So the motion would be of a sine wave that we have after t is equal to 3 pi, and this would go on infinitely because of the undamped conditions, right? This concludes our second part. Let's move on to the third part, right? So the third part states that we need to solve the ordinary differential equation and sketch the graph of the solution and compare the two graphs, right? So this ODE, I'm going to solve it using Laplacian, the tool Laplacian, right? So taking Laplacian both sides, derivative plus 16y is equal to Laplacian 4 times sigma del 3t minus 3 pi, right? Now using its linear property, we can distribute this. 16 comes out, y is equal to 4 times Laplacian del t minus 3 pi, right? Now there's a formula for the derivative, for the Laplacian of a derivative, and it goes something like this, that the Laplacian of y derivative is equal to the product of s into Laplacian of y minus the value of y at 0, right? Where s is basically our complex variable that comes in the definition of the Laplacian. So using this identity, if we try to find out the value of Laplacian of y derivative, it would be something like this, that s, the product of s and Laplacian of y derivative minus value of y derivative of 0, and substituting value of Laplacian of y derivative, we get that the Laplacian of y double derivative becomes s square Laplacian of y minus s times value of y at 0 minus the value of y derivative at 0. Now for this particular case, we know that the initial conditions are this, that both are 0 at t is equal to 0. So if we substitute this, both of these terms become 0. So all we are left is that Laplacian of y derivative is equal to s square Laplacian of y. So if we put this into the equation that we have found here, this becomes s square Laplacian of y plus 16 times Laplacian of y is equal to 4 times Laplacian of direct minus 3 pi, right? And taking Laplacian of y common, I get square plus 16 is equal to 4 times Laplacian of direct or del t minus 3 pi. Right, now let's focus on this term, that is Laplacian of direct delta. Now, just as I discussed before, the property of direct delta, that if there is a function that is multiplied with direct with a direct delta function, and the a is between the interval b and c, then this is equal to the value of g at a. Right, now from the definition of Laplacian, we know that of any function f is limit 0 to infinity integral e raised power minus st f t dt. Right, and dt is here also present. So if that function is direct delta function, then its Laplacian would be of this form. This is t, it's not clear, it's st direct t minus 3 pi dt. Now using this property, we get that this integral is nothing but e raised power minus 3 pi t. Or in general, if this 3 pi is a, then the general solution would be e raised power minus at. So let's substitute the value of that we have found. So just write a general line here, that Laplacian of del t minus a is e raised power minus at. So substituting this value using this formula that we found into this equation that we have, we get Laplacian of y s square plus 16 is equal to 4 times e raised power minus 3 pi t. So taking s square plus 16 in denominator, e raised power minus 3 pi t, and 4 upon s square plus 16 can be written as 4 square. This is what we have got now. Now this means that y is nothing but the Laplacian inverse of this that we have. Now this can be evaluated using the second shifting theorem, or the t shift or the time shift theorem that we have, time shift theorem, which states that Laplacian of a function that is the product of f t minus a function f that is shifted by a, and the heaviside function or unit step function u, is equal to e raised power minus at fs, where I'm gonna write where fs is Laplacian of the function f that we have. So this is the statement of the second the time shift theorem. This is what time shift theorem tells us. So basically ft minus a ut minus a is nothing but Laplacian inverse of e raised power minus at fs. This is we're gonna evaluate our y using this. Now if we carefully examine 4 divided by s square plus 4 square, 4 divided by s square plus 4 square, it can be compared with the general form omega s square plus omega square, and we know that Laplacian of sine omega t, and in this case omega is 4, Laplacian of sine omega t is omega s square plus omega square. So basically Laplacian of sine 4t is 4 upon s square plus 16 4 square, even better, right? So now since we have got this, using this second shift theorem, we get that y can be written as Laplacian inverse of e raised power minus 3 pi t Laplacian of sine 4t, and this can be written as, from this theorem, the function f is sine, this time sine 4 t minus 3 pi. On comparing, we get that a is 3 pi. A is, in this case, is 3 pi sine 4t minus a, and multiplied by the unit step function or the Heaviside function u t minus 3 pi. This is our solution, or the motion that this mass spring system exhibits. Now if we graph this, before graphing this, I'm going to simplify it a little bit. So this is sine 4t minus 12 pi ut minus 3 pi, and this can be written then as y is ut minus 3 pi, and sine that we have 4t minus 12, and taking the minus common and using the property, we basically get that y becomes ut minus 3 pi sine 4t. This is the simplified version, and if we graph this, we get that due to the Heaviside due to the unit step function, which I'm going to define, which is defined as that it has a value of 0 for t less than any value of t that is less than a, and 1 for any value greater than a. For any value greater than a, it is 1, and for any value less than a, it is 0. This is how the unit step function is defined. So before 3 pi, the value is 0 of y due to the Heaviside unit step function, and after this threshold of 3 pi, it follows the sine graph, the sine 4t graph, sine 4t wave, and this goes on infinitely to undamped condition. So this is our solution, the graph of a solution. If we compare it with what we had found in the second part, it approximates the same, like a sine graph after 3 pi and 0 before that, and the graphs that we have could estimated that could have been the answer, or made that could have been the answers. So the solution is this. This is our answer.